Okay, hopefully you can see my presentation. All right. Okay, cool. I see the chat. Um, so yeah, I'm Ciaran Ryan-Anderson. I guess I've already been introduced. I didn't hear that part due to maybe the audio issue. But today, basically, I'll be talking about some of our, like giving a high level overview of some of our more recent experimental QEC work that we've been doing over at Quantinuum. So we started doing experimental QEC back in 2021. And first at that time we had like 10 physical qubits. So we concentrated our work on like doing a single logical qubit and kind of all the little ingredients that like all the little protocols and ingredients that you'd want to do. Um, for a large scale fault tolerant device restricted to a distance 3 a single logical qubit. And so for that paper back in 2021 we were able to do like the first repeated rounds of QEC or syndrome extraction for a full distance 3 QEC code. We were able to make use of feed forwarding to actually do like adaptive syndrome extraction. So you only measure the set of operators that you need to in order to come up with corrections. And also all these, of course, had to, but yeah, all these corrections were determined in real time while we were running the experiment. So we were doing real-time decoding, which is currently quite difficult to do for most experimental devices, although Google has recently done it in their last paper. And eventually, a few years after that, we started looking at logical 2-qubit gates and starting to see them actually slightly outperform our physical 2-qubit gates if you kind of ignore putting in QEC, which does reduce the error rate a bit or increases the error rate a bit. And of course, from there, we want to scale up as the devices scale up. So like, look at higher distances, look at more logical qubits, demonstrate more complex decoding, and so on. So we've been on the path to do that. If I were to give this talk like a year ago, this is sort of the timeline I'd give of our work. And however, yeah, and these white, I don't know if you can see them on the timeline. These white dots kind of indicate some of our more recent work. So we've kind of been accelerating what we've been doing, largely because the devices have become more complex and more capable. And so we're now, initially we started with 10 physical qubits, and now we're up to 56 qubits. And our devices have like all-to-all connectivity, so we're able to move. Our technology is ion trap based, and we can move the ions around to different gating zones and interact them, arbitrarily between different qubits. So we can look at all sorts of QEC protocols and don't have to be worried about what you might have to be worried about with like a fixed 2D geometry. So here's a bunch of our experimental QEC papers, and all of these that I'm highlighting in this box are the stuff that's came out this year. So you can see we've actually done more, we put out more work this year than we have done in the last few years in the past. And all that's probably accelerated by, like I said, the increased capabilities of devices with more qubits, as well as we've been like maturing our software capability. And I'll talk more about that. I don't know what everybody's background is, whether everyone knows what QEC is about, but this is a very short, high-level introduction to that. So to kind of get an idea of like why we need quantum error correction and how does it kind of compare to what we do, with normal sort of classical devices like computers and whatnot. It's kind of interesting to see what the error rates were for different devices. So for example, back in the day, one of the first programmable electronic computers was the ENIAC device. It used a bunch of vacuum tubes to do calculations. And if you look at the literature and you calculate what their effective error rate is, they basically experienced one error per 10 to the 14 operations. And essentially what that meant is like a vacuum tube exploded and they would have to replace that vacuum tube to keep on going. And now, at least the data I was able to get was around 2008. But the transistors have an error rate you can work out to be about one error per 10 to the 28 operations. So that's a crazy amount of operations that you can do before, you might get a zero flipping to a one. Although things are starting to shrink and it's kind of getting to the regime where we now need more like classical error correction in our devices, like in our DRAM and stuff. But for the most part, there's not much classical error correction in the devices, except for large data centers and supercomputers. Those are necessary. They actually, like, the error rate that the supercomputers experience depends on like the altitude that they sit at was found, because what mainly affects them is actually cosmic rays and decays in their packaging. So yeah. And now quantum technology is around one error per 10 to the 3 or 1,000 operations. So that's not great. But of course, you can't directly compare these things because hopefully we'll get an exponential speed up, when we do these large fault tolerant devices. But it kind of gives you a perspective of how far classical computing is compared to where we are now. But there's a reason for that. The quantum world is kind of like this chaotic, crazy mess where things are rapidly interacting with each other. You kind of might imagine, from the atoms and electrons perspective, we're kind of like giants that are on the scale. Oh, I see. Would I prefer questions during the presentation or at the end? I don't, yeah, either way is fine. I'll try to keep track of the little pop-up chat bubble. It would be nice if the audio was working, but unfortunately, well, I can, yeah, deal with it. Anyway, so yeah, like the quantum world is rapidly interacting with each other. There's photons, bouncing around and it's a crazy mess. And what quantum hardware does is kind of like, isolate these things and keep things in order and stop the environment from interacting with your qubits. And then quantum error correction basically uses redundancy in order to get them all working together, and kind of like if one or two of the qubits are misbehaving due to errors, that the process still keeps on going, and hopefully you can correct those things fast enough. And quantum error correction is more difficult than classical error correction because it's a bit different, because we have to deal with stuff that arises due to the nature of quantum mechanics. So not only do we have to deal with bit flips like you have to deal with in the classical world, but we have to deal with phase flips, general rotations, crosstalk, where if you do some interaction, you might accidentally cause some small interaction between other parts of your device, leakage, which basically moves the qubits into a non-computational space, and so on. Also, there's this annoying property called the no cloning theorem, which means that we can't just like copy arbitrary states. So we can't just duplicate them and use that as a source of redundancy. And further, of course, like if you measure things, you'll collapse it to a classical state. So you can't just like peek at stuff arbitrarily. So if we had no cloning, but we had this measurement collapse, it'd be fine because we could just arbitrarily collapse it and then check things. But the two together make things more difficult and annoying. So what you have to, like some smart people like Steen and Shor and others, back in the day figured out is that you can construct the things so that you can coherently store your information. So you can take a single qubit and store that information multiple qubits across them, and construct the relationship between these qubits in such a way that you can measure observables that don't learn about the actual logical information that's stored in them, but instead you can like infer what might be going on. And maybe, yeah, and so you typically send these observables that you measure that give you indirect information about what the environment might be doing to your system are known as syndromes, and you typically send that information over to a classical algorithm to come up with a correction in order to with a high probability undo what the environment's doing to your system and protect it. Another annoying thing is that there's these no-go theorems that tell us that if you want to compute with these logical qubits and not just have them as fancy memory, unfortunately, there's no like universal protected set of gates that you get that's nice and straightforward. You have to do various tricks in order to get a universal gate set. All right, moving on from the like really fast, high-level introduction to QEC. I'll start talking about some of the stuff that we've been doing here. So before you might consider going and doing QEC, because QEC, because of it, it's utilizing this redundancy and has to, manipulate a large number of qubits in order to do the computation. The QEC requires a lot of overhead in the number of qubits and the time that it takes to do a computation. So it can be useful to kind of explore the space in between like physical qubits and full QEC and look at what's known as quantum error detecting codes. It can, you can potentially like use them to also sort of start learning about, like, because they require so much less resources typically, start learning about what it's like to do logical operations on physical operations and see how that plays out. So one of the codes that we look at is known as the iceberg code. So basically it uses 2 extra qubits in order to encode your logical qubits. So you only have an overhead of 2 qubits. But it's a distance 2 code. So what that means is that it can detect that something has gone wrong in the computation whenever you measure these observables, known as stabilizers, but it can't correct it. So basically you have to like halt your computation and reject that run. And so this can lead to you rejecting potentially many shots depending on the code and depending on your error rates. So it does add like basically time overhead or a low space overhead. You can't indefinitely use these sort of error detecting codes as you scale things up, because the number of shots that you need to take for an experiment will grow exponentially, since based on the number of qubits you have and the size of the code, or the size of the algorithm and so on. So that's a little disappointing, but we can actually start taking advantage of these things, and we've actually seen improvements using these error detecting codes. And also we've been pushing down our error rates more and more, and so the rejection rate at which we have to throw away shots has been reducing significantly. So for example, Kentaro Yamamoto and others at our Japan branch of Quantinuum, he's a quantum chemistry scientist, and he took the iceberg code and he looked at estimating the ground state energy of hydrogen. And he was able to find that the encoded version gave a far more accurate result and got close to the true value compared to the unencoded version. So that's an example of where we're seeing improvements using logical quantum error detecting codes. And then rather recently, in collaboration with JP Morgan Chase, we looked at applying the same code to a problem known as QA-OA. It's essentially an algorithm that is used to try to calculate an approximate solution to optimization problems. So like, you have a bunch of constraints and you're trying to satisfy as many constraints as possible. And it's typically an NP-complete problem for many. It depends on the problem itself, but often it can be NP-complete. So it's not something the quantum computer can solve, but you can approximate and get close to the optimal solution. And in that more complicated algorithm, they're once again able to see an improvement in the encoded version, kind of like represented by this orange line, compared to the unencoded version for certain sizes of the problem. Okay, moving in the other direction, as I mentioned, like we have this all-to-all connectivity because we can essentially move ions that represent our qubits around in our devices and interact them however we wish and quickly move them around. So we have effective all-to-all connectivity. Using that and a summer intern, Noah was able to implement a 4D surface code. So the surface code is a well-known code that probably many even outside of QEC knows about. Essentially, it looks kind of like a chessboard. It has these local checks, wait for checks that you measure. So simple, small local operators that you measure between qubits. And then there's a 3D version of that kind of looks like a bunch of cells. And then the 4D, is some other generalization past that. And there was an article about it, and this is some reporter conception of it, where they obviously used generative AI to show us what the fourth dimension looks like. Obviously, it doesn't actually look exactly like that. But basically, the key points of this paper is that it used our all-to-all connectivity, and we're able to go beyond just simple 2D codes. So kind of showing the power of these ion trap devices, and also this four-dimensional code had a property known as single-shot error correction. So often with a lot of codes, you have to repeat measuring these observables, these syndromes. Multiple times to deal with measurement errors. And this 4D code has enough redundancy so that you can just do one round of measurements instead of multiple rounds like typical. And so it has a single shot capability, which can potentially speed up doing your general computation. Yeah, and so he implemented this on our H2 device, which kind of looks like a racetrack. And this is the actual video of the ions kind of moving around because we can fluoresce them. So you can actually see those things zipping around the track. And we're also, so we started with, back in the day, and we still have them around, these linear traps where the ions kind of bounce around in a line. And we've moved since then to this racetrack kind of device where they can, now it's quasi-linear, still 1D, sort of. And we do have test stands where we are able to actually now build grids and move ions around in 2D. And so kind of moving in that direction where we'll have like large traps and we can move these things around and go from like a racetrack to kind of racing around in a city. And that should speed things up dramatically since it's much easier to sort and move ions around in a grid in 2D, then shuffling them around past each other in 1D. As I mentioned before, so it can, an important thing to study and work out if you want to compute on the logical level is how to do logical operations. And often it can be difficult to work these things out for various codes. Like there's been recently a lot of interest in what's known as high rate LDPC codes, because they can potentially greatly reduce the overheads of the number of qubits. However, those codes, a lot of them, it's difficult to work out what exact, how to gate with them, how to do logical operations with them. And not only that, you often need, in order to maintain the speed and the advantage of those codes, you also need to be able to compute a bunch of operations in parallel. And that can be sometimes a very difficult thing. So working out and figuring out how to do gating for different codes can be a difficult task. And so work by Simon, Burton, and others kind of looked at implementing gating in a new way. So a lot of people, as I mentioned, are familiar with the surface code. There's a related code where you basically take the surface code and put it on a torus. That's called a torque code. So these are well-known device or codes and well-studied. And in general, you can kind of think of these surface code-like codes belonging to a family of different topological objects that have different genuses. And so you start thinking about that, as well as maybe, modifying the set of operators that you measure. So like there are a set of, rules that stabilizers have to abide by. And some things that just don't work. And so if you kind of think about these different topologies, as well as like change the surface code based on, modifying their local stabilizers stuff, you can start making different variants of the code. And in particular, Simon and others looked at kind of morphing these codes further, kind of like taking two copies and kind of like kneading them together and mixing them around and getting these what's known as double covers, and actually finding that they enact a new 2-qubit gate. So yeah, in general, kind of sometimes you can get new things out of old stuff, old things that are known, by kind of abstracting it and kind of playing around with their properties. And so, yeah, essentially they created these new Clifford 2-qubit Clifford gates by braiding these genons. So these more kind of abstracted, generalized surface codes, and creating what's known as Dane twists. And this all is capable, or like they actually implemented some of these experiments, and we're capable of implementing these things, particularly because of our all-to-all connectivity. Okay, another important thing to consider whenever you're taking QEC and moving it from theory land to actually implementing it is you actually have to, of course, fix the errors and come up with corrections and apply them in real time as you go. And so that can potentially be a difficult task. Luckily, ions are relatively slower than some others. So it means that we have a lot of opportunity to do more complex hybrid compute, given our longer coherence times. So in the past, I mentioned before that we did do real-time decoding, so coming up with these corrections as we were doing the quantum computation, doing the error correction. But we utilize what's known as a lookup table. I think I actually have a picture. Yeah, it looks something like this. So we originally were using OpenChasm 2.0, an extended version of it, to allow more complex classical operations. And you could use it to embed essentially what's known as a lookup table. Lookup table is basically where you kind of like list you before doing the computation, you work out, given the different measurements, I'll see what are the corrections should I apply, and kind of storing that in a table and looking it up as you do the computation. That would be nice to do in principle. However, to compute these lookup tables, it becomes an exponentially hard task as the size of the codes grow, as well as, of course, it requires an exponentially large amount of memory. So eventually you can only get to a certain distance before you no longer can use lookup tables. So the general way that you want to get around this is by using algorithms and doing computing on the fly to work out your corrections. And the common kind of gold standard algorithm is known as minimum weight perfect matching. I think I wrote it wrong here. But that's a common algorithm that's used for like the surface code. Essentially, you're like trying to find trying to pair up syndromes that have flipped with the shortest path, because it's more likely that a smaller number of errors led to what you saw than a larger number of errors that could lead to the same sort of flips. So yeah, we've now I don't know, last year or two now have this more complex hybrid compute system where we basically have this classical computer that runs in parallel with our quantum computer, and we can use what's known as WebAssembly. It's not a protocol that we invented, but something that was invented for the web so that people could compile code and run it on other people's servers and not accidentally like take them down. So it's kind of sandboxed. So it's kind of a useful thing for us where we can allow users to create whatever decoder they want, and then then they compile that like C or Rust or C++ code to WebAssembly and submit it to us, and then it can run with guarantees that it won't take down our quantum computer, and they can essentially make function calls on this kind of compute environment. So as a sketch, it looks something like this. You write your quantum program and then separately compile and send your WASM code. And the quantum program basically makes function calls, and you can send arguments, variables over to the classical side and get back arguments. And so kind of these things are running in tandem and sending information back and forth. So eventually, you get out your ones and zeros. And yeah, so this is, a necessary step to do real-time quantum error correction for algorithmic computing or algorithmic decoding. And Natalie Brown, who actually is an alumni of your university, she went to there. She's currently has run experiments and currently writing up with the help of others, where we actually run minimum weight perfect matching on the surface code, and we do like these multiple rounds of cinder extraction for each copy of the surface code, and then do a 2-qubit gate and so on, and come up with the corrections and apply them in real time. And this is a big table of the results and the fidelities for doing basically spam for 2 qubits, then adding QEC gadget, like D rounds of cinder extraction, and then applying the CNOT with or without QEC, and then looking at whether you're just tracking the correction in software, which you can do for the most part until you hit a non-Clifford gate, and then you have to apply the correction or adapt to what you're doing, or actively applying the correction. So for the most part, getting for 2 logical qubits, getting between 1 and 2%, or I guess sometimes 3% error, which is divide that by 2 over D rounds to get the error rate per cinder extraction. So I don't know, divide that by 6, I guess. So relatively high fidelity, constantly, even for a given, once we make a device, we're constantly like improving and adjusting and changing the lasers and augmenting various things. So over time the error rates can come down. And yeah, kind of related to that, we need to move, to mature QEC, from, just ideas to actually starting implementing stuff and running logical algorithms like we're starting to do. We also need to look into logical tomography and verify that the QEC protocols are doing what we think we're doing. And how well are they performing? Are there, particular error sources that are causing problems and so on? So, for these experiments, I've been developing basically a logical level programming language, and QEC library, which is freely available and open to the public on GitHub. And using that, Carl Meyer, who his studies have been focused on tomography on physical qubits, is able to take that and construct QEC experiments where he looked at a variety of things. So he, in particular, he looked at applying T-gates. Let's see, let me step through these things. So the simplest thing is he looked at applying logical two-qubit gates. So this is, in particular, these are transversal gates. So you apply physical CNOT between two codes, and the physical CNOT goes from one qubit to the other corresponding qubit in each code. And so he did basically what's known as 2-qubit randomized benchmarking on the logical level. And yeah, saw a relatively high fidelity, so 99.91%, or 99.8%, depending on the device. So I looked at both the H1-1 device, which is that linear trap, and then H2-1, which is that racetrack. And he also looked at this T gadget. Let's see. So sorry. Here's the T-gate randomized benchmarking. Essentially, you apply the CNOTs as well as random single qubit Cliffords and repeat this a certain amount of time. And you can kind of look at the decay rate, and you're able to kind of extract the error rate or the average fidelity for that process. And for the T-gate, so you generate this magic, what's known as a magic state, which is a state like if your code can only compute with like Clifford gates, at least the CNOT and like Hadamard and S typically, you can get a universal gate set if you generate a resource state known as a magic state, which is basically this T-gate on a plus state. And then you have this gadget that allows you to teleport that gate onto the code. He looked at two different methods. One where it's kind of the traditional one where you apply the T-gate and then the state keeps on going, or a version where it's basically like that plus 1-bit teleportation all at the same time. So it teleports the state and applies the gate. And he found basically, he also looked at doing post-selection on the results of the measurement versus not. So the results of like measuring this measurement that gets rid of 1 of the qubits. And he found effectively that this method 2 version in experiment actually worked better. We didn't necessarily know that to be true a priori. And we believe that it's likely, like some of the reasons why it might be because there's leakage in the system. So whenever you apply these gates, there's some probability of the qubit going to this like non-computational state. And this teleportation thing essentially makes a fresh qubit and then moves the information onto it. So it might actually like reduce the amount of leakage in the system, or other non-qubit type errors that might be in the system. So by doing experiments, we actually saw that like one protocol was better than the other, which is useful information for improving things in the future. Yeah, and so they put those sort of things together, the CNOT gadget, which is needed for the T-gate, plus, single qubit Clifford gates that we can do on the Steen code. Sorry, I should have said you're using the Steen code, which is a distance 3 color code. It looks something like this over here. And so each one of these lines is a Steen code, and he essentially applied, these set of operations, and then was able to implement the quantum Fourier transform on the logical level, which is a necessary component for like doing phase estimation or for doing factoring, like Shor's algorithm. And so he got relatively high. He also did tomography, looking at like the state fidelity, and got relatively high fidelity for that, for as relatively complex algorithm for today, for nowadays for QEC. So around in the 80s to 90s percent fidelity for different states. Although some of them, it looks like there might be around 60 or 70. Where I think completely random is like 25%. All right. And then moving beyond that, another experiment that we recently did was logical teleportation. So once again, we're using the Steen codes thing, which is, as I mentioned, the distance 3 color code, which has 7 data qubits per logical qubit. And what we wanted to do is we wanted to teleport it, because teleportation is a potentially useful gadget in order to like move information, across, for example, a very large device. Say you have a future fault-tolerant quantum computer with 1 million qubits, and that potentially might be a very large device. So what you might want to do is like create Bell state resource states, could be individual physical Bell qubits, and send them across the device, and then use those to teleport like logical information across the device. And so this kind of gives you a background of how teleportation works in a kind of a very high level hand wavy way. But essentially, what's an important component is creating these Bell state resources, as I mentioned. Of course, the Bell state is this superposition of 0, 0 and plus 1, 1. And of course, one of the weird properties of quantum mechanics is that you can send like this, each qubit in the Bell state anywhere, like across the galaxy, measure them, and there always will be, both in 0 or both in 1. So as soon as you know the results of one, you know the outcome of the other. Which is, often called spooky action at a distance. So the idea of teleportation is that you use this resource state, this Bell state, and where you can potentially move one of the qubits somewhere else, where you want to teleport it to, and you bring in your general state that you've been computing with, for example, and we want to do all these at the logical level, so we need to do transversal operations and do the proper initialization of this code and so on. And then you have to entangle that logical qubit with one of the qubits in that Bell pair, and then measure that off, essentially apply the Hadamard and then measure it off. And it actually, what this does is if you actually push the Z operator backwards in time, you'll see that it turns into an X operator at this Hadamard, and then moves, branches out to an X and X operator. So essentially, this measurement up here is measuring the joint XX operation. So which is stabilizes the it stabilizes the Bell state. So Bell state is stabilized. We'll give it is a +1 eigenvalue state of XX. Similarly, if you push Z backwards, you'll get a Z here, and you'll go up and be a Z over here. And this is also the other stabilizer operator of the Bell state. So Bell state is also +1 eigenstate of the ZZ operation. So essentially, you're measuring these Bell operators. And I'm not going to do it here, but if you know about like stabilizer update rules, you can take the stabilizers of the Bell state and measure the two different stabilizers, and then do a poly correction on the other qubit of the Bell state, and find that the logical operator X and Z has to jump over, gets basically it gets it's gets enlarged. The logical operator moves down, and then has to, whenever you measure these things off, basically has to exist over here. And so you can work out with math that the logical operator has to jump over here, and that's essentially showing you that all the logical information moves from this area to this area for any general state. So basically, the important things are, as long as you create these resource states, however you do it, and you can do this potentially ahead of time. So you could use, for example, a lot of post selection in your large fault tolerant device in order to get a really clean state, and have a lot of like many factories doing these. So many copies that will generate with a high probability. You only have to do it a few times. A Bell state, move it around in your device, and then entangle it at the same time, entangle it with one of the other ones, and then just have to do local measurements. And so long as you can do classical information, you can basically move a general logical qubit with a speed as fast as you can move bits, which is basically the speed of light. So that's useful. Essentially, to do this logical experiment, we took our first experimental QEC results, where we implemented the Steen code on a single logical qubit, and then other results where we started looking at two logical qubits and doing logical 2-qubit gates, as well as this logical level coding language and QEC library. Combine that in order to implement it at teleportation at the logical level. But then we also went further. So all of that I explained, mainly showing these C naughts, where we're imagining these are C naughts being applied transversely, like I mentioned before, where you apply a physical C naught between these two code blocks for each of the 7 data qubits, corresponding 7 data qubits. So we did this transversal version of the experiment, where we prepare this Bell resource state, post-selected as much as possible, since you get to do that with the fault for a large scale fault tolerant device. And then the rest of the experiment, there's no post selection, because you're not allowed to really do that in general, unless it's scalable. But that's particularly rare set of situations. And yeah, entangled it and did teleport the qubit, logical qubit. But we did a version with or without an extra QEC gadget, where we do fault tolerance. We measure multiple rounds of cinder extraction here, or we didn't. It turns out also that this gadget, if you don't have this QEC gadget here, itself can be thought of as Keneal style cinder extraction. So this is a different way than sort of the canonical way that people think about usually of doing quantum error correction, where because you're measuring these two measurements basically allow you to measure the X channel and the Z channel of this logical qubit that you're computing with, and come up with corrections. And so the teleported qubit will actually be corrected for any changes in syndromes that have occurred since you've last done quantum error correction. And so this overall thing is on its own a QEC gadget as well. And so this can potentially be useful because it allows you to kind of trade space for time, because it also basically turns any CSS code, or you could do it in other ways with non-CSS codes, but it's easier with CSS codes. Turn any like surface code or color code or whatever into a single shot a code that you can do single shot on, because you just measure one round of each of the data qubits. So you measure all 7 data qubits up here at this measurement, and all 7 data qubits down here. And essentially, you can do that in parallel, and basically with one round, do measure all your information and construct and work out what the syndromes would have been, because you're essentially collapsing things to an X basis classical code and a Z basis classical code, and then coming up with corrections that will both correct this original qubit as well as teleport it down. So yeah, by introducing additional logical ancillas, you can basically speed things up and trade space for time. So it can potentially be useful in a device that has arbitrary connectivity or far flexible connectivity than nearest neighbor interactions, which allow you to do this transversal gate operation. In addition to that, we also did a lattice surgery version of this code. So lattice surgery is basically where you take codes, these like surface codes or color codes, and kind of measure them together, kind of fuse the codes together by measuring operators between the boundaries. And that allows you to effectively measure joint poly operators. So we also did this experimentally. It turns out that this effectively, you can see, like, if you think about how the stabilizers work, the zeros are stabilized by the Z operator, like plus Z operator. And so these already have the joint ZZ operator stabilizing them. And so if you measure the XX operator and then make a correction, then you have created a Bell state, because you've enforced a ZZ or plus ZZ and plus XX operator to be to stabilize the state, to force the state to be a +1 eigenstate of both of those operators. And then we needed to do these Bell state measurements I mentioned before, where you measure joint ZZ and joint XX operators, and you can do that here by doing this joint ZZ operator measurement by doing lattice surgery, and then measuring off the 2 qubits in the X basis. And so that's equivalent to getting the logical XX information and the logical ZZ information. So this does exactly the same thing as this, but we're using a different gate set where we're measuring and fusing codes across boundaries and then potentially splitting them. And so we're one of the first also to do lattice surgery experimentally. And then another kind of interesting thing about lattice surgery is because it's a different gate set, and essentially it's doing logical parity measurements. Often you can take algorithms and you can express them more efficiently in lattice surgery. And so that's sort of what we did, is we showed how you could take this and see that there's a hidden parity measurement with this middle qubit basically acting as an ancilla that's measuring parity across these 2 logical qubits. And arrive at this lattice surgery circuit. It is effectively, though, doing what's known as 1-bit teleportation, where you don't get the advantage of being able to like teleport the information across to any place in the system, but you get to move the information from this logical qubit down. And you're essentially just like fusing the 2 codes together and then kind of deleting the other half of the code. You can think of it that way too. So we did all these different variants of it. I did a bunch of optimization to really bring down the error rate of the first 2 experiments. I had less time to kind of optimize the lattice surgery stuff, but we kind of see the results of these experiments here in this graph. These are all the infidelity, or basically 1 minus the fidelity, or in other words, the logical error rate. This is the physical implementation. So this gray bar is known as the process infidelity. It's basically the same thing as the average of these. So, sorry, let me back up a little bit. for each one of these experiments, as well as the physical version of this experiment, we sent in as our general qubit a zero, logical zero state, +1, plus, minus, plus I, minus I. And then we calculate the fidelity by measuring in the same basis. So the Z basis, the X basis, and then the Y basis. And saw what is the probability of getting the state that we prepared and the output that we should get from that, from teleporting it. And from that, we can work out the fidelity for the individual states. And the average of that is basically this transparent bar, this black boundary, and then the process infidelity is related by that by multiplying it by some constant. So effectively, you can just look at these different bars represent the different basis states. So blue is 0, orange is 1, green is plus, red is minus, and so on. And we can see basically what is Keneal's cinder extraction is within error bars the same as the physical error rate for doing this teleportation. You can also see the Z basis has much lower error rate, and that's because we have memory error in the system that's kind of biased in the Z direction. All of this has been done, these experiments were done like a year ago, and the memory error in our system has become much better. And so I'd imagine if we were to rerun these experiments, these bars would become much closer, not equaling to, but much closer to the Z basis stuff over here. So we probably surpassed the physical version of this experiment. But then the other versions being more complex and having more circuitry, and sometimes not having as much attention in optimizing stuff at different levels, have unfortunately higher error rates. But I imagine those are largely those could be largely brought down by more attention and more optimization. But yeah, essentially, we're now able to do QEC at a really low error rate and also teleport the qubits at the same time, which is kind of cool. And yeah, all the fidelity, I guess, is around what, 99 or better, 99 point whatever percent. I don't know. Unfortunately, I don't have the table. But yeah, I basically went into why all this is useful. Yeah, gives you single shot quantum error correction if you want. Can also remove all sorts of non-qubity errors like leakage. And yeah, and allows for high connectivity. And allows you to trade space for time and so on. It also allows you to pretend as though you're doing research that will enable Star Trek or whatever. All right. So this looks like let's see. Yeah, I guess we're getting basically at the end. This is our roadmap. We're constantly improving the devices. As I mentioned, we're going from these linear devices to these kind of racetrack devices to something a bit more complex with this kind of X junction in the middle of kind of a racetrack, and then up to these much larger devices with grids that allows us to move qubits around and sort them quickly. So I imagine as we do more, get more and more qubits, and some of these devices are coming on soon, that we'll be able to do more and more complex QEC with them. And yeah, basically done. Yeah, you can get access to these devices if you're interested via, like, Oak Ridge has a program where you don't actually have to spend money. You just have to like submit some sort of grant thing. You can also, I think, get some credits from Microsoft Azure. You can go get access to our devices through there. But also, if you're close to graduating, we're constantly hiring, so feel free to reach out or look at our job page or email me and whatnot. But yeah, thanks for listening.
Thank you. Can you hear?
Yeah, there's a lot of reverberation though.
Can you hear me?
Okay,
Hello?
that's a lot better. Yeah, I can hear
All right,
you.
thank you. Can we have a round of applause for him real quick? Yeah, so I guess we'll take questions now. Yeah. Does anyone have a question? If not, I can ask something. Can you hear me all right, by the way?
Yeah, I can hear you fine.
Okay, can you guys hear this? Could you say something quickly?
Testing, testing. Can you hear me?
Can you guys hear this all right? Okay. You want to
Yeah, I was gonna ask, I guess like coming into quantum computing, like what background do you think you had that helped, and like what background do you think you lack that you had to obtain while working in the field?
Sure. I mean, what I did my PhD in is in quantum error correction. So, I mean, I'm still doing quantum error correction, so that helped a lot. But back in the day, there weren't really any tools for simulating or like modeling QEC and so on. So during my PhD, I had to do a lot of programming and whatnot, and so. I've gotten pretty decent at it. Sometimes people think I'm a software engineer, but I'm not. Um, so, and I think also, we're getting to a state where we're doing very early QEC experiments, but eventually we need to actually implement, these large architectures where we have to compile, go from, a description of the algorithms that people want to run to actually compiling to a target like QEC architecture. And so I think that like requires a lot of software skills potentially, but I think though there's also like having a background in like hardware or tomography or just doing, very theoretical mathy things is also just fine. There's a variety, like QEC, like quantum computing in general is a very interdisciplinary field, but I think QEC itself is quite interdisciplinary too. So, yeah.
All right, thank you.
Any other questions I can ask? A bit more of a technical question. So I know that you guys probably do a lot of simulation, like simulating your noise models before running them on hardware. Is there a specific like framework or methodology? Like, do you use like Markov chains and stochastic processes, or like operator models? Like, how do you model noise if you were simulating it?
Yeah. So unfortunately, I didn't like describe too much of the hardware. But one thing that's nice about our systems is I think they're fairly easily simulatable because essentially we really like keep all these ions far apart from each other and then only bring them together whenever they need to interact. And so they're interacting in particular well-defined gate zones. So we don't have a ton of like crosstalk and whatnot. So the way we simulate things, basically I use the code that I had been working ever since graduate school. So there's, hope for if you're working on stuff now, tools now that, you can get and, reuse them in your own work if go somewhere else. Um, but using those tools, what we mainly do, most of the error modeling is basically Monte Carlo type error modeling, where we're, running through each individual shot. And we're applying, for the most part, stochastic noise. There is, so it's relatively simple, but it models the device, like what the tomography says about our device, well. There are some bias noises in even the stochastic model that we use, but there's also like coherent noise that we model as well. So you have to like apply rotations about the z-axis, for example, dependent on like the time that you're doing transport and so on. So I take, for example, we have a compiler written by the compiler team. It spits out operations that the actual ion traps run on, and so I intercept that, or I take that and then convert, extract all the information about where the qubits are, in order to apply crosstalk correctly, and also apply leakage and apply the memory error according to the time that things are transporting around or idling. So the error modeling itself is rather simple, but there's a lot of details to it.
Any other questions, Heather? Ask another. I like to ask this question whenever we have a speaker who's in quantum computing or quantum error correction in particular. There's a lot of companies like, Oxford Ionics and Alice and Bob that will say that their devices are going to be able to work with really high fidelities without requiring quantum error correction. Do you personally believe that that's a realistic outlook, or do you think that we could get to that stage, or do you think we'll always need some form of error correction?
Yeah, I don't know what I've heard. I've heard this before from some groups, and it raises my eyebrows. uh, I think I like for some applications, I have seen that like people might only need to get to 10 to the minus 6 error rate in order to do some interesting like quantum simulations. But of course, we're always going to want to do much deeper algorithms. Some stuff that requires 10 to the minus 12, 10 to the minus, whatever, and we'll constantly want to push it. So I doubt that devices are going to get, I don't know, much better than 10 to the minus 6, maybe if they can even get to that. So I think even if, Microsoft, whenever they were pursuing Majorana fermions, they thought they could, back in the day, get to 10 to the minus 9. But they still expected to do quantum error correction because, you still need to suppress noise past that. So I'm very doubtful, but who knows? I don't know everything, but I'm fairly doubtful that you'll be able to do everything without uh for some things you'll definitely need QEC at least. Maybe there will be other things where you don't, but those are limited applications probably.
Yeah, so as like a corollary to that last question.
Yeah, wait, we have another question.
So related to that last question, are there any like physical limits or other like engineering limits that we can use to like reasonably predict how low error rates can get in the near future? Like say 10, 20 years?
Yeah, that's a good question, but that might be kind of outside of my knowledge because that's more of like an experimentalist question of what are the fundamental limits. I think as far as like we're at least, kind of by osmosis know, talking to experimentalists on our side, what sort of error rates we're kind of expecting. And I think probably like the 2-qubit gate, I think we're imagining that it gets down to 1 times 10 to the minus 4, but I don't know if those are fundamental limits. I think I've heard that like microwaves might be able to get down lower. Who knows? Maybe lasers can still get, so maybe at least for ions, maybe it's 10 to the minus 4, 10 to the minus 5, maybe 10 to the minus 6, but that might be hard. Who knows? But I don't know. I'm not a reliable source for what are the fundamental limitations for those things.
Any other questions?
I guess how does knowing the physical like structure of like the ions, like since you're using like trapped ions, for example, I mean sorry, of the qubits, since using trapped ions, how does that affect how you approach the programming, I guess? I know it might be too general of a question, but
Yeah, could you maybe unpack what you mean? What sort of programming do you mean?
How do you do error correction?
yeah, like how's the error?
Yeah, he means like how do you change how you do error correction based on the fact that you're using trapped ions?
Yeah, I mean, for example, we're starting to look at, older ideas. Like back in the day, people were just trying to work out how do you even do quantum error correction. And so Keneal, for example, had a bunch of ideas of, using a bunch of resource states and doing these like Keneal style teleportation QEC gadgets. And those I don't think have been looked at very seriously for a while because we started thinking more in kind of the superconducting mindset in QEC where everything kind of in fixed 2D geometry. But now things I think are a lot more open. And so in some ways it's a little scary for me working with ions because it's a huge design space. Since you do have a very flexible connectivity, you might not expect like as the device gets towards millions of qubits that you'll use all-to-all connectivity, but it's still quite flexible in being able to move qubits. But yeah, by kind of thinking about this, it kind of like makes you think about other alternatives that you might want to do, like Keneal style symbol extraction or other ideas and so on. Yeah, and also like sorry, and also like other codes, for example, like it's much easier for us to do codes that are have long distance interactions, like for example that 4D code you couldn't easily do on a 2D fixed geometry. So we'll be looking at the advantages of more general codes. Like I like the color code because it allows you to have access to all the Clifford operations and speeds things up. But there might be like a super color code where it has more complex interactions that don't just fit in nicely in a 2D geometry. We might look at that instead.
Any other questions? If you have, oh wait, yeah. Do you have a bit more time? By the way, we have one or two
Yeah,
more
no,
questions.
no worries.
Okay. Yeah.
Yeah, sorry, I think I might have gone a bit later than I meant
No,
to.
you're fine. You're fine. It was great to hear everything. Yeah.
Thank you. Thank you very much for the nice talk. So I have a question about. So you mentioned a lot about maybe a little bit about error detection, and there apparently is some post selection that happening there. So to me, it feels like this approach is not scalable to like
Yeah.
arbitrary resource, right? It seems like only
Yeah.
work for. So do you? But in terms of this, like how much post selection is happening currently in those quantum error correction results?
Yeah.
Like I'm just curious because sometimes people are not quite clear about that in the paper. Can you just make more like I'm trying to learn more about it.
Yeah, no worries. Yeah, I mean, we tried to make sure that what we do is kind of with what we need to do for large scale fault tolerant things in mind. And so we do for the experiments I mentioned here, a bit of post-selection, but it's for resource states. And so that has been known as something that you can do in a scalable fashion, where you're basically producing these states on the side that will later be consumed by the main computation. And you can prepare like try to prepare a few copies in parallel so that you have a very high probability of having the resource state ready for the computation to consume. And that's something that you need to do anyway with like magic states and stuff. There is a balance, like you might of course there's always like space-time balances and optimizations that you might have to consider in the future. And so you might want, even with those resource states, you might not want to, like, obviously as the distance grows, the probability that something one of the checks fails or something grows exponentially. But so you might want to balance how much resource post selection you're doing versus not. But still in general it's perfectly valid for resource states, and that's where we're doing it. We're not doing post selection the rest of the like actual circuit where you compute.
I see. Great. Thank you.
Any other questions? I have a question. So we, like here at Georgia Tech, we have like a lot of undergraduates and graduate students, and we're trying to work on, like implementing stabilizer codes and testing them on hardware, benchmarking them and all of that. So like one of our like biggest avenue, or what two of our biggest avenues are just like creating noise models, and then one of our main interests is actually trying to figure out how we can optimize how often you do a QEC cycle during an algorithm. So we have a couple of students that are working on, like how can we optimize that, and like study it using noise models, like based on like gate count, circuit depth, gate time, all of those sort of things. Like besides that, or if you have any like critique for that idea, or do you have any other avenues that you think are particularly interesting for quantum error correction that you think undergraduate and graduate students can pursue just like as a research project?
I mean, all that sounds great. I mean, it's stuff that we're also interested in doing. And also if it's useful, a lot of our like tomography data where you can use to build error model, like we use it for our own error modeling, is out there in the public. But yeah, I think in general, I think for quite a while, people have been focused more on the theory, and there's a lot of devils in the details. And so, working towards actually implementing different ideas and seeing, fleshing those out, and then, yeah, optimizing it, because there's like this notion of like XREC fault tolerance, which is a nice mathematical framework, but in practice you might want to reduce the amount of error correction you're doing because it actually isn't helping you that much. Or like with ion traps, for example, the memory error is so good that it doesn't make sense to do a bunch of repeated rounds of error correction over and over again, because you're actually going to inject more noise than you're kind of resetting the coherent curve. Other devices, though, that might be more useful because they have much shorter coherence times. But yeah, I think fleshing out ideas and playing around with error models and implementing stuff is a great place to look at. Those are definitely like skills that are going to be needed in the future. And then besides that, like skills that are needed is like, it is kind of like I think there's many different avenues that are going to be useful. So like I mentioned, like even if if you have a more hardware bent stuff, that might be useful in like constructing better error models or optimizing devices for QEC and so on. Or more theoretical, searching for codes or whatnot, or other protocols that are more efficient. But I think another important area is like developing software, compiling QEC algorithms. I think probably it's a large field that hasn't really been studied yet, and should exist, of how to optimally compile QEC. Yeah, I don't know. Sounds like you guys are going in a good direction.
Yeah, thanks. Any last questions? If not, another round of applause for Ciaran. And yeah, it was great having you. So yeah, is it fine if we send out this recording to the rest of our association for other people to watch? Yeah,
No
okay,
worries.
great. Yeah, okay,
thanks.
thank you. Yeah.
And thanks a lot for having me talk. Thanks.
Yeah, thank you for giving the talk. It was really great and great learning experience. So yeah, talk to
Thanks.
you later.
Bye.
Bye.